Okay, so in order to work with inclines, we need to take a quick review of forces we've learned thus far. Okay, so first of all, our normal force. Okay, thus far we've looked at normal force as going in what direction? Up, right? It goes up. Okay, we need to kind of reconsider that into thinking that the normal force is the surface pushing back up on the object. Okay, so the normal force has to be perpendicular to this surface. Okay, so thus far we've worked with surfaces that are flat, correct? Okay, so if our surface was here, then our normal force always went straight up, right? That's perpendicular. So if we're working on an incline, then our normal force will be going in this direction. Okay, it's perpendicular to that surface. Okay, so now we have to kind of reconsider what our normal force means. It doesn't always mean it goes straight up. It means it goes perpendicular to that surface. Any questions about that? Okay. What about gravitational force? In what direction does it always go? Down. It always goes down. Okay, it always goes straight down. So it has nothing to do with the surface. It has nothing to do with surrounding objects. It always pulls it straight down. Okay, so when we're working with inclines, we have to rotate our axes. Okay, the reason that we rotate our axes is because if we don't, we're going to have a ton of forces that we have to break into components. And we don't want to do that. Okay, so we rotate our axes to go along that incline. Okay, so here, my incline is like this, so that means my x-axis will go just like this white line. My y-axis will go here. Okay? So do you think that the bottom of the incline or the top of the incline should be the positive direction? The bottom. Okay, so down is positive. So that's how we would label our new coordinate system. We just kind of shift it to the right a little bit. All right? Down the incline would be positive, because if something's sitting on an incline, it's most likely going to go down, right? So we want that to be the positive direction. Okay? Okay, so everything's at kind of a shifted angle here. Okay, since we know that the force of gravity points straight down, we need to take a little examination of the force of gravity now. We know gravity for this would point straight down like that. Okay, the normal force would go perpendicular to the surface like that, like such. Okay, so this would be our normal force. This would be our gravitational force. All right, so now we have two new forces that we're going to look at here. Gravity is technically at an angle here. If we look at our axes being along with the incline, gravity is technically at an angle. So what we do is we make our gravitational force broken down into components. Okay, and these components have specific names. This horizontal component of the gravitational force is called force parallel. Okay, so we have two parallel lines that represent that. That's force parallel. Why do you think it's named force parallel? Because it's parallel to the incline. It's parallel to the axes or parallel to the incline. Okay? And then this force, this y component of the gravitational force, we also call the normal force. Why would we call it that? Any idea? Why we would call these two forces the same thing? Yeah, because they're equal. Okay, they go in the same direction, they're equal. So that means this normal force below the axes has to equal the normal force above the axes. Okay? Because this object on the incline is not going to be moving up and down, right? It's not going to be bouncing. It's just going to be sliding. So those are our two new components of our gravitational force then. We have force parallel and we have the normal force. How would we solve for these variables? Yeah, we just use our trig function. Okay? What's going to happen is that we'll be given an angle that the incline is sitting at. So let's say that this incline is at a 38-degree angle. Okay? That means this angle corresponds to this angle of our triangle. So whenever we find the angle of an incline, we know it always goes at this top angle right here. Okay, so if I were to define force parallel in this situation, I would take sine or cosine of 38. Sine of 38 equals F parallel over what? F sub g, because that's our hypotenuse. Yeah, we can calculate F sub g in any equation if we have the mass. Right, so that's going to be used a lot of times, and we'll have that hypotenuse of the triangle. Okay, any questions thus far? All right, we're just going to jump in and do problems then. Let's go ahead and get this problem written down, and then we'll walk it through step by step. Diagram would look like? Not quite? Let's draw it. Okay. Here's our incline. For some reason, I always draw my inclines in that direction. You could go the other way if you want to, but I just always do. Okay? So here's our object. What forces do we know have to be acting? Gravity. Oops. And the normal. Okay. All right, so if we have F sub g here, and we have, this is our normal force, what do we have to break down F sub g into? F sub parallel goes here. F sub n goes there. So F sub n is also always our vertical component of gravity, and parallel is always our horizontal component. All right, what else do we know for this problem? We know the angle. Okay, so this angle right here is 30 degrees. All right. So, what do you think the first step should be here? Yeah, we're going to find F sub g first. And to find F sub g, we take mass times gravity. (98 newtons). Okay, that's our F sub g. So that will then be our hypotenuse of our triangle. Okay, so we found our force due to gravity. Now we need to find our normal force. I'm going to draw just an abbreviated version of our gravity triangle here. Oh, that's not good. Okay. How do we calculate our normal force? Yeah, we know this angle right here is 30 degrees. So we want to find the normal force. What'd you get for your parallel force? Normal. Sorry, I labeled this wrong. This should be F normal. That's my fault. 84. Okay, we'll just round it to 9. 84.9 newtons. Okay, this is our normal force right here. 84.9. Okay? Questions about that? All right. Now we want to find the parallel force. So to find our parallel force, we're going to use sine this time. What'd you get? 49. Okay. So this is kind of the order we can go in. You can do these steps you can do these problems in almost any order. I'm just going in what I think is the easiest. Okay? So our overall goal here is to find acceleration down the incline. Okay, so if we look at our incline and we look at the acceleration that this object is experiencing, is it in the x direction or in the y direction? X, yeah. It's in the positive x direction because it's sliding this way. And we chose this down to be our positive direction. So we want to find F net of vertical components or of horizontal components. Horizontal. So tell me what rightward horizontal components we have. Yeah, F parallel. Do we have any leftward horizontal components? No. You can put 0, you can leave it off. If we had friction, this is where friction would go. You'd subtract out friction, but we don't have that. Okay, so our F net has to just equal our parallel force. What did we get for our parallel force then? 49 newtons. Okay, we can substitute here F net for mass times acceleration. We know that our mass is 10 kilograms. We divide it out to solve for acceleration, and we get 4.9 meters per second. Squared. So as you read this problem, what are you solving for? What's your overall goal here? Time. Overall goal is time. In order to get there, we are going to have to find acceleration. Overall goal is time, but yes, you will need acceleration to get there. Fair enough. All right. It's fine. We're good. Okay. So here's our incline.
It's okay, Zig.
Here's our object. For some reason, our object is always a green box because that's all that I can draw. So what's this 466 telling us?
It's weight.
Yeah, it's weight. It's weight. Or it's F sub g. Okay, so let's go ahead and draw all of our forces here. Here's F sub g. Here's our F sub n. And then we'll break our gravity down into components here. The bottom force is called what?
Parallel.
Force parallel. And this is called the normal. Okay, this is the other side of our normal force. Okay? Do we need to solve for Fg, or is Fg given to us? Okay, so Fg we know is 466. Okay, so we can take that part out of the problem. Okay, we can go ahead and solve for the normal force. If we want to solve for normal force, we're always going to use cosine. Okay, so we're going to take 466 times cosine of 33.3. Okay, what'd you get for your normal force? 389.5. Okay? Now we want to look at acceleration in the horizontal direction or the vertical direction. Horizontal. So more importantly, we need to solve for the parallel force rather than the normal force. Okay? So let's go ahead and solve for parallel.
So do we even need to find our normal?
That's all right. It's okay. When we have friction, you'll need to solve for normal force. So it's not a bad habit to just solve for it anyway. Okay. So our parallel, we're going to take 466 times sine of 33.3. And we get what? 255.8 is going to equal our force parallel. Okay. So in our net diagram here, in our force net, what rightward forces do we have? Just F parallel, right? Do we have any leftward forces? No. So our net force then equals 255.8. And we can make our substitution here for mass times acceleration equals 255.8. And we know that our mass is... What do we know that our mass is?
47.6.
How'd you find 47.5? Yeah, we take our F sub g and we know that this equals mass times gravity. So we take this mass times 9.8 and we divide 466 by 9.8 and we get our mass to be 47.6. So now we can plug in our mass back down here, 47.6 times acceleration, and you have your acceleration equal to... Okay. Are you done? No, you're not. Okay, you still have to solve for time. Okay, so in order to do that, we need to go back to our kinematics equations, and I'll give you these equations, but the one you're going to use is x equals x sub o plus v sub o t plus 1/2 at squared. And you want to solve for time. Alright, so for your time you got what? 1.77 seconds. 1.77 seconds. So we have the same type of situation. We have a box on an incline. This time we have friction. Okay, we want to find the horizontal acceleration of this object. Okay, so we'll draw our free body diagram here. Force of gravity going down, the normal force will go up, perpendicular to the surface. Then we have to break our gravity down into its respective components. What other force here am I missing? Yeah, friction. Friction is going to be opposing that velocity or the acceleration, so friction is going to go up the incline. So I'll label my forces here, force of friction. This is F sub g. The bottom force is always called what?
Parallel.
Parallel, good. It's our normal. Okay. So we want to find our overall horizontal acceleration is our goal. So if we know that's our goal, do we need to solve for the normal force? What if we have friction? Yes. So in this case we do. Even though we're working with horizontals, we still have to solve for the normal force. Okay, so we need to find both components of that triangle. Okay, so which would you like to solve for first? Yeah, let's solve for F sub g first. That's a good idea. 20 times 9.8. Wait, 196 or 4? What did you say? 196. Okay. Okay, that's our F sub g. So now we can start moving on to components. Which one? F sub n first, okay? We're going to use cosine here, so we're going to take 196 times cosine of 50. Okay? Does everyone understand this shortcut I'm doing here rather than writing it out as a fraction and multiplying it? I'm just simplifying. Okay, great. So we get our parallel force to equal what? 126. Okay. And for our parallel force here, we take 196 times sine of 50. 150.1. Okay. So now if we're looking at our net horizontal force, are we missing one part of it? Friction. Let's solve for frictional force. So F sub F is going to be our coefficient of kinetic friction here times our normal force. So we'll plug these in here. Our coefficient we know because it's given is 0.4 times our normal force, which we calculated to be 126. So our frictional force is what? 50.4. The point's kind of stuck behind there. Okay. So now we can go over and write our F net equation. Okay. So F net, we're going to take all of our rightward forces minus our leftward forces. So we have rightward forces are what? F parallel. Do we have any more rightward forces? What about left? Force of friction. Very good. Okay. So then we can do our substitutions. Our mass is 20. We're going to take that times our acceleration, which we're trying to solve for. Our parallel force we calculated to be 150.1. Our frictional force we calculated to be 50.4. So that means 20A equals what? 100.99.7. And our acceleration would then be yeah, 5 meters per second squared.